So now I'm going to talk about the formation of the secondary haemostatic plug. You might be wondering why you need the secondary haemostatic plug when you've got the primary haemostatic plug. Well, the secondary haemostatic plug involves the conversion of fibrinogen to fibrin. Now, fibrinogen is already binding two platelets together. However, fibrin is a large sticky net which holds together everything in the blood, so that's red blood cells, white blood cells, proteins, and anything else that's passing by. So this essentially turns your primary haemostatic plug into something much bigger to prevent bleeding. So the coagulation cascade is how you convert this fibrinogen to fibrin, and it's made up through a number of steps, which you can break down into three simple pathways. You have the extrinsic, intrinsic, and common pathways. So the extrinsic pathway is triggered by external damage to a vessel, so this is penetrating damage to a vessel or something of that sort. Intrinsic pathway is triggered by internal damage, so this is to do with the build-up of plaques on the wall of arteries and things like that. And then the common pathway is triggered by your extrinsic and intrinsic pathways, and this is where they come together to form the common pathway. And these are the final steps of the conversion of fibrinogen to fibrin. So the extrinsic pathway, as I said, is caused by disruption of the endothelium, and you get the release of tissue factor, which is held within this endothelium. Tissue factor is then has the role of converting factor 7 to factor 7A, and factor 7A then converts factor 10 to factor 10A. So the A here stands for activation. So essentially, tissue factor activates factor 7, and factor 7A activates factor 10. And that's as simple as the extrinsic pathway is. The intrinsic pathway is slightly longer, but still fairly simple. So you have contact activation. So this is where the wall of the artery has become roughened, and this causes a series of reactions which activates factor 12, which is floating around in the blood. So factor 12 is activated by this contact activation, and then that itself triggers the activation of factor 11. That causes the activation of factor 9, and that causes the activation of factor 10. So what you'll notice here is that it's 12, 11, 9, 10. So if you count down, for some reason 9 and 10 are in the wrong order, but other than that, it's not too difficult to remember. And you'll also notice that the final step of both of these pathways was the conversion of factor 10 to factor 10A, and this is the first step in our common pathway. So our common pathway involves the conversion of prothrombin to thrombin by factor 10A, and it's worth noting that prothrombin is also known as factor 2, and thrombin factor 2A, and fibrinogen is factor 1, and fibrin is factor 1A. And thrombin causes this conversion of fibrinogen to fibrin, where fibrinogen is our substance holding together two platelets, and fibrin is the big sticky net causing a large clot. So if we put these together, we have the formation of the whole coagulation cascade, where you have the intrinsic pathway on the left, where contact activation causes the activation of 12, which causes the activation of 11, which causes the activation of 9, which causes the activation of 10. Or you have the extrinsic pathway, where external damage leads to the release of tissue factor, which activates factor 7, which activates factor 10. You then finally have the common pathway, where your activated factor 10 activates your prothrombin to thrombin, and then your thrombin converts your fibrinogen to fibrin to give you your secondary haemostatic plug. Now again, we have some medications which affect this process, the first of which is our warfarin. So warfarin's mechanism of action is as a vitamin K pathway antagonist. So this means it prevents the vitamin K pathway. Now 4 of our factors, which are 10, 9, 7 and 2, are dependent on vitamin K to form, which means if you prevent the vitamin K pathway from taking place, you prevent the formation of these factors, and therefore you prevent the blood from clotting effectively. So one handy way to remember this process is by remembering that the vitamin K pathway is 1972. Now, there you have to remember that the 1 at the start stands for 10, but other than that, it can be a handy way of remembering things. It's also worth noting that in block 3, you'll come across the 1973 for remembering the parasympathetic cranial nerves. But the helpful way to remember this is block 2, so it's 1972, and that's block 3, 1973. So we also have the heparins. So their role is to upregulate something called antithrombin. And unsurprisingly, one of the actions of antithrombin is to inhibit the action of thrombin. Also, slightly strangely, it has the double action of also sometimes inhibiting factor 10 and its conversion to factor 10A. So there are two different types of heparin. We have low molecular weight heparins, and if you think of the fact they're low molecular weight, they're sort of the basic ones, so they only affect one of these things. So they prevent the conversion of factor 10 to factor 10A, and unfractionated heparins are more advanced, and they prevent the conversion of factor 10 to factor 10A, and they prevent the conversion of prothrombin to thrombin. Finally, we have the direct thrombin inhibitors, which pretty much do what it says on the tin. They inhibit thrombin and its action of converting fibrinogen to fibrin, and the example on your drugs list is dabigatran. So we can now put that all together into one easy to remember slide. So we have the intrinsic pathway, where we have the activation from contact internally, leading to the activation of 12, 11, 9, and then 10. And we have the extrinsic pathway, which involves the exposure of tissue factor, which activates 7, which activates 10. We then move on to the common pathway, where our activated factor 10 converts prothrombin to thrombin, and our thrombin then converts fibrinogen to fibrin. We then have some medications which affect this. So those with the orange stars next to them are our vitamin K dependent factors, and these are the ones that if you take warfarin, you'll be deficient in, and therefore your blood will not clot as effectively. We also have our heparins, which are low molecular weight heparin and unfractionated heparin, and they affect antithrombin and the different types of antithrombin. And low molecular weight heparin causes the inhibition of factor 10A, and unfractionated heparin inhibits both factor 10A and inhibits thrombin. Finally, we have dabigatran, which is our direct thrombin inhibitor, and that prevents thrombin from converting fibrinogen to fibrin. And that is essentially the formation of your secondary hemostatic plug. Thank you.